This video will begin our discussion of equations of lines in space. Will be a little bit different than lines in 2 space. So let's begin with this. I'm going to put a random green line in 3 space. There are numbers on here, but we're not going to pay attention to the numbers. I have my green line, and then I'm going to let V be a vector that points in the direction of my line. Okay, so I'm going to write out my logic following to this equation. This is going to be the theory behind why the equation of a line is the equation of a line. Okay, so since line L, we'll call this L here, since L is parallel to vector V, then we can create a vector that represents the line, but as a vector. So I'm going to call this vector, let's call it vector W. No, let's just call it, let's actually name it. Sorry about that. Vector, and then we're going to put the vector of the line. All right, it's going to be a weird way to kind of describe this, but I can actually describe this vector as a line by taking a multiple t and multiplying it by my vector v. All right, this creates that line over time t. Right, if time is 0, I'm at 0, 0. And this is just a vector. This isn't the line itself, right? So this is that vector describing the green line, right? It could be anywhere. Remember, vectors don't live anywhere in space, so I could put anywhere on that green line. But over time t, I can represent that line. Okay, so we're going to pick 2 points on that line. So given, and we're going to name them here and give them names, or give them components. So P naught, or P sub 0, is going to be X naught, Y naught, Z naught. Okay, and then any other point, sorry for that weird Y, any other point, and we'll call this P, and we'll just call it X, Y, Z. This is going to be, P naught is our specific point in our reasoning, and P is going to be, XYZ is going to be our generic point. So that's where we're going to get X's and Y's from, is our generic point. Okay, so I can then also describe this vector on that line as something else as well using my 2 points. If I have a terminal point and an initial point, I can subtract them and get a vector. So it's going to be X minus X naught for my X component, Y minus Y naught for the Y component, and Z minus Z naught for the Z component. Okay, all we have done so far is we said, hey, I have a line in space, and I have a vector that can describe that change in that line, and we set up a vector here, and then we're setting up another vector there. All right, so one last thing, and then we can actually do a little bit of algebra. We're going to give vector V components. We'll call it A, B, C for vector V. This is going to be something we're going to use often. This is going to be the directional vector. This describes the way the line moves. This is, in a way, our slope of our line. All right, well, if I have 2 vectors and they represent the same thing, that means I can set them equal. So I'm going to take X minus X naught, Y minus Y naught, Z minus Z naught, and I'm going to set it equal to T times V, which is A, B, C. All we did is we described the same vector on that line 2 different ways, and now we're setting them equal. And you can see that we actually, for this to be equal, okay, we got to multiply the t through. So I guess I'll do that. I'm going to be lazy here and copy and paste. All right, and then I got AT, BT, CT. For 2 vectors to be equal, each component has to be equal. So I got X minus X naught equals AT. I have Y minus Y naught equals BT. And I have Z minus Z naught equal to CT. Notice I can solve for each one here. Okay, so we have X equals X naught plus AT, Y equals Y naught plus BT, and z equals z naught plus ct. Notice that all three of those look like mx plus b, where t is the variable. And x, y naught, and z naught are my b's. Those are where x starts, where y starts, where z starts. And then a is how x grows, b is how y grows, and c is how z grows. All right, so I'm going to write a line here, a statement here that we're going to rely on quite a bit. If I want an equation of a line, for an equation of a line, we need a point, x naught, y naught, z naught, and our slope or directional vector, v, and that is ABC. So as long as I have those two things, I can write the equation of a line. Now we have two different things, or equations of a line. Notice that we have three equations that represent this line. It will never be one. I need you to get that into your head because you're going to get it mixed up, I already know, with planes in 3 space. So make sure that you are keeping straight that an equation of lines requires two different sets up. It'll never be one equation. So this is what I mean by that. The first way we can represent a line is with what we call parametric equations. This is what we just came up with, and we represent it like this. Okay, we use a brace, and then we just say x equals x naught plus at, y equals y naught plus bt, and z equals z naught plus ct. Those are parametric equations. I also want you to notice that we can solve each one of those for t. Okay, so if I solve the x equation for t, I get t equals x minus x naught over a. For the second equation, if I solve for t, I get y minus y naught over b. And then t equals for z minus z naught over c. We actually have another way to represent a line using this. Notice those are all equal to t. These are called symmetric equations. And we write one equality all the way across. X minus x naught over a equals y minus y naught over b equals z minus z naught over c. Those are our parametric equations. I don't think that's going to fix for me. So these are our parametric equations. So we have only two different ways. I can't get my box to work. I'm going to leave it like that. To represent an equations of a line. We either have parametric equations, we'll have to have three describing x, y, and z, or symmetric equations that are written like that. Notice that the x naught, y naught, z naught represents the point on the line. The numbers in the denominators, a, b, and c, is our directional vector.